Hi everyone, welcome to seventh live session of this course. Okay, so today we are going to discuss about a bit, not a bit actually. Today we are going to discuss about continuity. Especially today we will focus on uniform continuity things. Okay, so okay, so first we shall start with the definition, then we gradually solve problems. Okay, so yeah, so yeah, okay, so let me share the screen. Yeah. So, well, just hold a second. Let me hide the taskbar as well. Yeah. So, yeah, I hope everybody can see the screen. Okay. So today, okay. So let's. Sorry. So let's do the definition of continuity. Definition of uniform continuity. Let I subset of R be an interval, and a function f I to R be a map. It's not continuous. It just be a map. Then this f is said to be then f is said to be uniformly continuous on I if for any epsilon greater than 0 we can find a positive delta such that for any xy in I with mod x minus y less than delta implies mod fx minus fy less than delta epsilon. If this property holds, then we say that the function is uniformly continuous. So graphically, what does it mean? Graphically, it means that if a function is uniformly continuous, then suppose for example, choose y equal to x square, this curve. Okay. So for by definition, what it tells? It tells that for any epsilon, we can find a delta such that any two points having distance less than delta, the points fx and fy are distance between fx and fy less than epsilon. Okay. So now consider this curve y equal x square. Consider 2 points. And suppose consider the two small intervals. Okay. Now consider these lines. So this means what? If any point lie in this region, then its image will lie this region. But on the top portion, consider small neighborhood and consider this. And then this neighborhood that this line cuts in the x-axis are relatively small. Okay, so here the delta are actually changing. So y equal to x square, it is not uniformly continuous. So intuitively it means that we can get some fixed delta for which this relation holds. I mean, this delta will work for any 2 points having distance less than epsilon. Okay, So this is the uniform continuity, and so obviously uniform continuity implies continuity. Okay. So consider the following example, because obviously examples are important. Without just going with theory, there's no point of doing real analysis. Okay. So first consider for an example, fx equal to 1 by x greater than 1. We check that if uniformly continuous. How do it? So just first calculate mod fx minus f. So this is what this is, mod x minus y by mod x. So anyway, this is less than equal to mod x minus s. So basically mod fx minus fy less than equal to mod x minus. Okay. So choose an epsilon greater than 0 and choose delta equal to epsilon. So if mod x minus y less than epsilon, this implies what? Mod fx minus y less than epsilon. So this implies what? So f uniformly continuous. Okay. On 1. So the next question which I should tell is that yeah. So actually it's the following counterexample. So soon we shall see that soon we shall show that x square is not uniformly continuous. But for the time being, consider the following question. Take f x equal x square, x belongs to 1. So that f is uniformly continuous on any closed interval. Show that it is continuous on any closed interval. Okay. How do it? So consider this mod f x1 minus mod f x1 square x2 square. This is what this is mod x1 minus x2 into mod x1 plus x2. Anyway, this is less than equal to mod b. I mean, this is less than equal to b mod x1 minus x2. So obviously, if delta equal to epsilon, I mean, so if mod x minus 1 less than epsilon, then sorry this delta, then mod fx minus less than epsilon. Implies what? This implies uniformly continuous. Yeah. So what is so what we're doing here basically? So basically here we are doing that the main first activity is that mod x minus minus x square into mod x1 minus to mod x1 minus x2. This is less than to be mod x1 minus x2. So if take delta equal to epsilon by 2b, then mod x1 minus delta implies, I mean, this less than delta which is equal to epsilon by 2b mod fx minus 1 less than it's uniformly continuous. Now, so what? These are the following. Now there are some theorems which we are going to use without proof. Okay. Now the importance of that theorem is that, uh, well, so okay, so this theorem can be used actually in or to prove that some function, this given function is irreducible or not. Okay, directly there is no use of the these two theorem which I am going to write. Okay, so let me substitute. Yeah. So suppose t subset of r a function d to r is uniformly continuous on if and only if for every pair of sequence in UN and P and in D, fine. Mod UN minus V mod implies mod f of UN minus f of Vn equals. Okay. So yeah, it is not equally supposed to 0. Okay. Basically, what is saying? Suppose D is subset of R and a function f from D to R is uniformly continuous on D if and only for every pair of sequence even in UN and D with this definite with this distance between UN and V goes to 0. Mod if n or mod if n mod UN minus fn goes to 0. Okay, so those who are going to watch it on YouTube, so they may think about it for a while. I said wait 5 minutes, then we shall prove it. Okay, so I shall be back after 5 minutes. Yeah. So, uh, so so this can be done as follows. Okay, actually this is a theorem, but uh, it can be done directly by using def directly by using the definition of continuity. Okay. So since mod u minus v n goes to 0. So mod u n minus v n delta less than for all n greater than equal to n. These will mod u f of u n minus f of v n less than star for all n greater than n. This implies what? This implies, I mean, yeah. So basically, the sequence fun minus fvn converges to 0 at n tends to infinity. Okay. So basically, here we are using definitions. Okay. Nothing more than that. So, yeah. So sorry, I'm thinking about something. So I realized, okay. So that one goes okay. So anyway, so yeah, so this is one theorem. So what is the application? One of its application is yeah. So so the fx squared is not fully continuous. So consider sequence even Vn in R. Vn is equal to n plus 1 by n. Vn is equal to v mod even minus Vn goes to 0. But even square minus Vn square is equal to what? 2 plus 1 by n square. That does not go to 0. Yeah. So even is equal to n plus Vn is equal to n. Then mod even minus mod Vn goes to 0. Fine. I mean, yeah, because of 1 by n, but what about u square minus v square is equal to 2 plus 1 minus does not goes to 0. Okay. So this way you can show that the function is continuous. So please go through it once again. I shall get back after 2 minutes. Okay. So going to the next problem. So there is one theorem which tells that if I is an interval and if I to R uniformly continuous function on R, sorry, on I, then f is continuous. We have already noted earlier the uniformly continuous implies continuous. So this is obvious, right? Okay. And there is one theorem. So this tells the continuous. So this theorem tells that this uniformly continuous implies continuity. So when continuity implies uniform continuity. So this theorem says suppose A is closed AB, that is compact. If sum of inner compactness is implies compact, and if I to R be continuous map. If uniformly continuous. Okay. So this is another theorem. I hope that sir has done this proof in class. Okay. So there's another theorem. Actually, the thing is, you might wonder the why I'm showing this theorem, but the point is that uh, one second. But the point is that actually these theorems are quite useful in order to show something is uniform continuous or not, because directly by using definition it is not always possible to show that some function is uniformly continuous or not. Okay, these theorems are will use act as tools. That's why. Okay, there is another theorem which states that suppose d is absolute bar and a function f d to r uniformly continuous. Then this theorem tells action is quotient d if action is Cauchy in. Okay. So this one, if uniformly continuous, then uniformly continuous map sends cos sequence to Cauchy square. So, and there is another theorem which tells that let I be bounded interval if I to R will be continuous on I. And if bounded on I. So okay, so I don't know whether sir has done this proof on or not in the class, but anyway, let's see how to prove it. Okay, so on the contrary, assume if not bounded. Okay, this implies what? For any n belongs to n, there is sequence xn such that mod xn mod fxn goes to n for all n. Okay. Now capital is bounded, so it has a subsequence. So capital bounded, so it has a convergence subsequence. So let by Bolzanov theorem. So let xrn be its convergence subsequence. So mod f greater than equal to n. Okay. So mod fxn greater than n. Okay. Now fxn is a convergence sequence. Fxn Cauchy sequence. I mean xn convergence. So xrn Cauchy. This implies f xrn Cauchy sequence. But this thing tells what? This thing tells f not bounded. So f can't be Cauchy. Yeah, that's it. So bounded on I. Okay. So now consider the following example. So till now what? Till now we have first introduced definition and we have continued. Then we have introduced some theorem and two or three examples. Okay. Now we shall go for the exam. Now we shall go for the yeah examples. But by the way, let me switch. Let me off the screen because probably there is some internet issue. So it's better to switch off the switch off my camera. Well, so wait for 2-3 minutes. I shall uh, get back within 2-3 minutes. Okay. Yeah. So for actually I was searching the my notebook. Sorry for the late. Okay. So the first example that we shall consider is that consider the following example. So the function fx equal to sine 1 by x. X belongs to open 0 1. Show that if not, one second, let me open my webcam. I hope the internet back came back come back. Yeah. So show that f is not uniformly continuous. So what is if x is equal to sine of x, x belongs to open 0, we need to check that if it is not uniformly continuous. Okay. So in order to show this, we will use the Cauchy criterion. Yeah. So one of the possible hint is the sequential criterion. Yeah, is the sequential criterion. So one thing I think I should say is this theorem is known as sequential criterion of uniform criterion. Logically, can you hear me? Logically, can you hear me? Logically, can you understand the things that are going on? Yeah. Okay, so it seems that she is not replying. I don't know why. Anyway, so this criteria is called the sequential criteria of uniform convergence, and yeah, that's it. So if x equals sine 1 by x, x plus open 0, we need to check that f is non-uniform continuous. So put take xn is equal to 2 by n pi, and obviously xn goes to 0, so xn Cauchy. Now if 2 by n pi is equal to sine n pi by 2, what is the sequence? The sequence of 1, 0, minus 1, 0, 1, minus 1, 0. So this is obviously not Cauchy. So if is not if is if is not uniformly continuous. Okay. So in this way, you can use sequential criteria. So what we have done first, we have choose the sequence x equal to 2 by n pi. Then we observe that 2 by n pi is a constant sequence minus 1 0 minus 1 0 minus 1 0 1. So this sequence, this actually sequence criteria. Also, moreover, observe that under these conditions, if is splitting one of those, I mean, yeah, sorry, what I said, I didn't get it. No splitting. So, yeah, so what I'm trying to say, sorry, I forgot. Uh, Please don't mind, but I could not remember actually. Yeah, for this reason, it's not uniform continuous. Okay. Yeah, we have choose the sequence 2 by n pi, and we just then observe that it is positive because it's convergent. Then we try to show that if 2 by n, if 2 by n pi is 0. Okay. Lavashari, please go through the solution again. I shall wait for 2 3 minutes. Then we shall start solving next problem. Okay. Please go through the solution once. So, Loshit, I think I hope this solution is clear to you. Okay, so let's go to the next problem. So, consider the function f x equal to 1 by x. Open 0 and show that if not uniformly continuous. Here we will also Loshit, please try the solution once. I solution on it. Then, if you can't solve it, then we will look at solutions problem. Okay, please try it once. Okay, so here the same similarity. Choose xn plus 1 is equal to 1 by n plus 1 goes to 0. So this is numerical continuous, but f of xn is equal to n, which is not uniform continuous. So you will convert. No, so xn plus 1 is convergent, Cauchy, and fn plus 1 is not convergent, so not Cauchy. So f uniform continuous by sequential criterion. Okay. So these are some examples. Now, well, so there's one kind of theorem. A function f on an open bounded interval if the f is uniformly continuous on AB if and only if limit x goes to a plus f and limit x goes to a minus f exist finite. So this one tells that if function is given open interval, then it will be continuous on there. If around the limiting value of the both sides are finite. This is a theorem. Now how to use it? So one second, how do you do it? Yeah, so for example, consider the function x goes to 1. Okay. And now consider open interval 0. But out of that, limit x goes to 0. This is infinite. So this function is not uniformly continuous on open 0. Okay. So yeah. Okay, so there are some one there's a one function that we need to find. Okay, so please go through the solution 1 to once again. I shall wait for 2-3 minutes, and please let me know if you're confusion or not. If you have no confusion, then we shall go to the next question. Okay. I shall wait for 2-3 minutes. I shall come back after 2 minutes. Okay. Okay, so there's one problem that I think we should find. So, sorry. So suppose A subset of R. Define a function dAx to be infimum of mod x minus A belongs to A. This means what? Suppose this our say capital A, x be a random point, then we will look at this infimum distance. So this is a definition of the function. Now observe that. By the way, this is known as the distance function. The one that is not related to noun mod BAX minus BBX. And exactly due to this inequality, this function equal to dx is uniformly continuous. Okay. So this is one function which is uniformly continuous. So so the how the graph of the functions look. Suppose we have some a of like this. So on the reportion a, it will be exactly 0. And there it will increase gradually. Remember, these are in continuous function but not differentiable. So this is one type of function that I think is. Then let's see. Okay, then solve some let's solve some problems. There is nothing, no more theory but left. Okay, so Logoswari, please let me know. Do you have any confusion and doubts in this distance function section? Please let me know. I shall wait for 2-3 minutes. Okay. Digi, can you hear me? Digi, can you hear me? Anyway, so let's start some problems. Okay. So also this following problem. Let C belongs to R and F R to R. We continue at C. And given that, and for free positive delta, there exists point one. Free positive C minus delta. If for equals to that if C equal to 0. Okay. So this theorem tells this. So this exercise which tells that f is a continuous function is continuous at C, and suppose for any delta greater than 0, that is in any small neighborhood around C, if we choose there always we get a point y such that f y is equal to 0. Then we show that f c is equal to 0. So how to do it? Visual logistically, can you please try? Visual logistically, can you please try? I don't know what the issue. Anyway. So suppose f c not 0. So it's we I mean by method of contradiction. So let f c not 0. So obviously either greater than 0 so I'll assume f c is greater than 0. So by neighborhood property, we can find a delta such that in this neighborhood c plus delta and c minus delta c plus delta, sign of f remains same. Okay. But so this implies what? F of y is greater than 0 for all y belongs to V delta C. Okay. But this contradicts our hypothesis. So FC has to be equal to 0. So this is one application. Excuse me, log study. Can you hear me? So actually, the point is that from last 4 or 5 lectures, I've seen that you are not responding at all. So I don't know what's the issue. Please respond. Okay. Yes, there is no point of keeping yourself joined in this meeting. So, so let's explain it once again. So this problem says C is a real number if is a real value continuous function at C. And suppose that for any positive delta, there's the point. There's a point in delta neighborhood of C such that FC is equal to 0. We need to check that FC is equal to 0. So we will use the method of contradiction. Okay. So assume that FC not 0. And let it is greater than 0. So when neighborhood property, we can find the delta such that C minus delta, C plus delta. In this region, the sign of f remains same. So in this region, f was greater than 0 for all viable delta delta C, which contradicts our hypothesis. So fc equal to 0. So this is one problem. So I shall over. So before start next problem, if you have any confusion or question, please let me know. I shall get back after 2 minutes. After 2 minutes, please let me know if you are any issue at all. If not, then we will start from the next problem. Okay. Okay. So consider the following problem. I hope Logan you don't have any confusion. Right. So consider the following problem. Okay. Yeah. Oh, one second. Sorry, there's some issue with graphic tablet driver, that's why. So, cause of following problems, then suppose if R2 are continuous. A point C belongs to R, said to be a fixed point if if C equal to C equals. To prove that, several fixed points of F in a closed set. So we need to basically show that several fixed points are closed set. So, alright. So define a function. So if this problem is actually can be solved by using defining a new function like this: gx equal to fx minus x. So if c equal to, so for those x, so I mean, so x equal to fx if and only g equal to gx equal to g. So this implies what? This implies we need to find those x as that g x belongs to g inverse 0. Now any the point is g continuous and singleton 0. So G inverse 0 is a closed set. So x has that x equal to fx is a closed set. Okay. So going to the next problem. Yeah, okay. So consider this problem. If R2 are continuous ones and let me explain that set x prove that the set x has that fx not equal to mu is open set. For the question f is R2 a continuous function, you need to show that all those x such that fx not equal to mu is an open set. Okay. So how to approach this type of problem? Is it similar as the previous one? So, so define a function gx is equal to fx minus p. Now x, I mean now if x not equal to mu, if and only if dx not equal to 0. So this is essentially those x as that this x doesn't have g inverse 0. So this is essentially the complement of this set g inverse 0. Okay. Now 0 closed. So g inverse 0 closed. So g inverse 0 its complement is open. Okay. So in this way you can prove it. So this implies what? And this is nothing but x as the fx not equal to is open set. Okay. So yeah, so this is one problem. So the next problem. So the next problem, one second. So the next problem. Okay. So this will be a very nice problem. Consider the map defined and closed in a region 1 real world function continuous integer. And if h only rational value in 0, that if is continuous. So this tells what? Suppose we have a continuous function 0 1 to r, and it has been told that f takes only rational values. We need to show that f is continuous. Sorry, f is constant. How do it? So the main technical tool that we need to use the intermediate value property. Okay. So basically the solution is like that. The solution is follows. Okay, so suppose if not constant. So theory. So if assumes. So let if I mean for choose total numbers. Assume that without loss R1 as well. So you can find an irrational number in between R1 and R2. And by intermediate value property, if assume the value with a contradiction. So if what contradiction? Why? Because it is given that if assumes only rational value, so f has to be constant. Okay. So okay, so yeah, so the next problem will be on the is on the intermediate value property. So let f into r equals or and x1, x2, x3 belongs to a. So that here exists c belongs to a such that fc is equal to fx1, fx2, fx3, fx1, fx2, fx3 by 3. So this is this can be using the interval algebra. So how we so choose a point PQ from AB such that if P less than equal to Fx if for all x belongs to open. So now, so obviously fp is equal to x1 f x2 3 by 3 is equal to f. So by intermediate value property, there exists C says that fx1 x3 I use alternative calculation. And not only this, alternatively we can show that fc is equal to f of x1 plus f of x2 plus f of x in by n for some c in the domain. Okay, so yeah, so Logisha, please go through it. Come back. Okay. Okay, so okay, so okay, so the what are the next problem? Yeah, also this following problem. So if be continuous and zero and f0 equal to f2, show that there exists a point C to close 0 1 so that fc is equal to fc plus 1. So So, yeah, as one may guess, here we need to choose a function gx is equal to fx minus f of x plus. Now observe one thing that, what about g0? G0 is equal to f0 minus f1. What about, and what about g1? G1 is equal to f1 minus f2. But if f2 is equal to f0 given, so f1 minus f0. So this is what? This implies g1, g0 is less than 0. Means so g is a continuous function, and so in between, by Bolzano-Versus theorem, in between 0 and 1, there is some point x naught such that gx naught, this is what this implies, fx naught is equal to fx naught plus 1 for some x naught. So this is what we want to prove, right? So so yeah. So yeah, in this problem, this sort of can be solved. So so the next problem, yeah. So one thing we need to recall is that if f is continuous function, then f of limit xn is equal to limit fxn. Okay. So using this, there is a problem. Suppose f uh, suppose it be real world. Okay. And let f restricted to q is 0. Show that fixed equilibrium for all x belongs to R. So, and obviously here f is continuous. So what the question tells? So this question tells that f is a real world function, and given that and if restricted over q is 0 map, and obviously f is continuous, we need to check that f is a 0 everywhere. So once again, someone was trying to learn. Oh, so yeah. Ah, okay. Sorry. Probably due to some issue. I don't know what happened. Yeah, now is my screen visible?
Yeah, yes, sir, it is visible.
Yeah. How long it was not visible?
Sir, I just joined it now, sir.
Okay. So there is another. So Logeshwari, can you please tell me how long the screen was not visible? Okay. Okay, thanks, Ravi. Okay, so Ravi, look at this question. The question tells that suppose f is a real world function and f restricted over q is 0, and given that f is continuous, we need to show that fx is 0 for all x belongs to R. Okay. So can you please try how to solve it? Hmm?
Yeah, yes, yes.
Yeah, do you have any idea how to solve this type of problem? Let me know.
Sir, here f by g is 0 or what it is?
Sorry, I didn't get you.
F by g is in 0 by 0 form or what?
No. F restricted to q means the value of f.
Achha, achha, okay,
Okay.
okay.
Okay. Yeah. Okay. Yeah. Okay. 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 Okay.
Sir, I don't know, sir. We
Okay,
shall
no
proceed.
issue, no issue. So the point is that here you need to use this following fact that if a function is continuous, then the limit can we can put the limit outside by taking it from inside. Okay, that is f of limit n tend to infinity xl is equal to limit n tend to infinity f of xl. Okay, so now in this solution, so if we choose any x from real number, so there is a sequence of rational numbers. Rn goes to q due to density property. Okay, so basically f of Rn goes to f of x because due to continuity of f, and f of Rn is 0, so f of x equal to 0. Okay, so Ravi, do you understand?
Yeah, hello, sir.
Yeah, do you understand this?
Sir, in between, like voice was breaking, so I didn't get.
Sorry, can you be louder?
Sir, I there was matlab, signal breaking or something, so I didn't get.
Oh, okay. So I let me
So,
repeat
sir,
this.
please once again go through. No?
Yes, sure. So we need to check that f is 0 everywhere. Okay. So we are choosing a point x from real number. Okay. So due to density of rationals, we can find a sequence Rn in rationals such that Rn converges to x. Okay. Till now you understand everything?
Yes, sir.
Okay. So now since f is continuous, so the sequence Frn will converge to fx. Correct? You understood? Okay. Yeah, thanks for typing in chat. So fx is a zero map. So now you understand the solution because each Frn is zero because we have already given that f restricted over q is zero. Sorry. Where someone's trying to join actually. Yeah, Ravi. So do you understand the solution now? Ravi, are you there?
Yes, sir.
Yeah, okay. So you understood this?
This density, like at
Yeah.
which place where did we use this Q?
Yeah. Due to density, we'll get a sequence of rationals in Q sequence rationals such that the sequence of rational converges to X. Okay. Now, due to continuity of F, the sequence Frn will converge to Fx. Now, the point is that since F restricted over Q is zero map, so for each n F of Rn is zero, correct? Because we have given that F restricted Q is zero. So basically, Fx is zero.
So, sir, this is zero at each and every x point.
Sorry, I didn't get you actually.
This f of x is zero at each and every value of x.
Yes. But obviously, we first choose a small x, then we are showing that this is zero. So basically, that since x is arbitrary, so f is zero for any x. Okay.
Yes, sir. Okay.
Okay. So, one second. Yeah, now comes to the following problem. So, f minus 1 to 1 r continuous at 0. Now, if fx is equal to fx square for all x belongs to minus 1, then show that fx equal to f0 for all x belongs to minus 1. So let me read out the question. F is a map from minus 1 to 1 to real, which is continuous at 0 is given. And assume that fx equal to f of x square. It is throughout the domain. Then we need to show that fx is nothing but f0 for all x belongs to minus 1 to 1. So Ravi or Jayant, can you please try it? And please let me know if you uh, can address this problem. I shall wait for 2 minutes. Okay. Please try this problem. This problem does not use any extra things of continuity. You just only use that sequential criteria of continuity. So you use the sequential criteria of continuity and try to solve this problem. Okay. Please try.
Sir, how to begin with this question?
Oh,
Like how to start?
yeah. So let me give the hint. So choose the C belongs to minus 1 to 1 and consider the sequence C to the power 2 to the power n. Okay. Now on this sequence C to the power 2 to the power n, use the sequential criteria.
Sir, I don't know, sir.
I at least try for some seconds. I mean, you
Sir,
try.
this like x of n we are using x power n, that sequence xn.
No, there is no sequence is there. I in the hint I have written down sequence. You need to use that sequence in order to show that FC is something. Okay. Okay. Well, so yeah. So point is that since fx equal to fx square given, obviously fc equal to fc square. Also fc square equal to fc to the power fc to the power fc to the power 2. With fc to the power 2 to the power 2. Similarly, fc to the power 2 to the power 2 is equal to fc to the power 2 to the power 3. So basically, this tells that fc is equal to fc to the power 2 to the power n or all n. So this implies what now? This c to the power 2 to the power n goes to 0 because c belongs to minus 1 to 1. So this implies what? fc is equal to f0. You understand the solution? Let's go through it.
Yes, sir.
Yeah, okay, thank you. Good.
Sir, this f of c equals to f of 0.
Yeah.
Like, matlab, how would we conclude over this?
I mean, since c to the power 2 to the power goes to 0, that's why f c to the power 2 to the power n goes to f of 0, right? Correct?
Okay, for -1 to 1 only. Yes, yes.
Yeah, the
In that
function.
range.
Yeah, if it's defined on that range only.
Hmm.
So,
Yes, sir. It was a good question. This is a. Sir,
yeah.
what is the purpose of this sequential criteria in that continuous function?
Okay, the main purpose is
How,
to.
how is it different from the limit definition?
Okay, the sequential criteria for the limit tells that suppose limit fxn is equal to L. Okay, sorry. Yeah. Suppose limit x goes to c fx is equal to L. Okay. This is equivalent to saying for any sequence xn converges to c, the sequence fxn goes to L. But limit x goes to c fxn fx equal to fc means for all sequence xn goes to c, fxn goes to fc. These are the equivalent definitions, and the major difference is that in the limit, in the definition of limit, this limiting point, that is x belongs to c, this c may not belong to the domain, but in the continuity definition this c has to belong to it.
Sir, the first one is which one, sir, that first case.
Yeah, limit, it is a limit definition, limit.
Okay. In limit definition, the C cannot be in the domain.
No, it is not cannot be, it may not be in the domain.
Yeah, may not be.
But in continuity case, the limiting point has must belong to in the domain by definition.
I mean, for that, it's closed. That range
No,
interval should be closed.
yeah, I mean, it may not be closed, but I mean, you can choose the open. You can consider open intervals, right? So the point should be inside the open interval. That's the point here. Okay. I mean, the continuity does not talk about anything outside the domain. That's it. Okay. Understand? Ravi? Understand? I mean to say, Suppose if this function defined -1 to 1, okay, x goes to x, then obviously limit x goes to 1, fx, this makes sense, and this will be 1. But since
Okay,
1
so
is not in the domain, so we can't talk about continuity of f at the point 1. That's the point here, okay? So that's the, I mean, that's the structural no, difference. That's it, okay? So, now the next problem. Okay, the next problem is as follows. So let f 01 to 01 continuous on this. Prove that there is C belongs to 01 such that fc is equal to c. So basically, this function is from 01 to 01. They told that fc has to be equal to c. Okay. I mean, look at graphically at least. So I mean, it is 0 and this is 1 point. Okay, and this is the line fx equal to x. So this tells that any continuous function would cut this line at least once. Okay. So I mean, if you try to draw a continuous graph, so I mean, obviously it will cut because if f0 is something greater than 0, so this graph will like look like this, and then f1 1, then okay, and if f1 is not 1, then it will this point, right? So at any cost, fc has to be equal to c. Intuitively, it is clear, but how to prove it? So well, so Ruby, do you get the intuition?
sir, what is the question again?
Yeah, the question is that if the function from 01 to 01, which is continuous on its domain, we need to show we can find a c such that fc is equal to c.
Sir, there is one theorem, na? Intermediate theorem, yeah, some theorem is there. For a continuous function, if f of a equals to f of b, then there will lie one c such that f dash equals to 0.
No, it is continuity problem. It is not differentiability problem. Okay, right?
Achha, achha, okay.
So can you try this? Or at least can you have the intuition? Look, I mean, solving problem is important, but also you need to get some intuition. Okay. So can you? I mean, can do you get the intuition that okay, it should be the case. So do you get the intuition? Please let me know. Please let me know, Ravi.
Yeah, sir, for a straight line, like this is valid when y equals to x.
Sorry, I didn't get it. Yeah, yeah. I mean,
For a
obviously,
straight line,
yeah, I mean, obviously for a straight line it is obvious, but for any condition it should be the case. Because if f0 is not 0 and f1 is not 1, so f0 will lie some top portion and f1 will lie some bottom portion, okay? So then if you try to join, then obviously this has to cut, right? I mean, it's intuitively clear, it should cut, correct?
yes, sir.
Understand?
Sir, if you take sin x function, right?
Sorry, which function?
Sir, sin x function, matlab there
Okay,
will
sir.
be one curve.
Yeah. Look at the graph of the sin x. How the graph of sin x look like? This will looks like this, right? Sorry. The x, I mean the fx equal to x line curve sin x in this way. So anyway, there is a one intersection, correct? At least on the first portion, there is a one intersection, correct?
Yep. Yes, sir.
Understood?
Yes, sir.
Yeah. Okay. So how to prove it? Okay. So, oh sorry. Oh, one second. I don't know what's happening. So I mean, so assume f0 non-zero and f1 not equal to 1. So obviously f0 is greater than 0 and f1 is less than 1, correct? Now consider the function gx is equal to fx minus x. So now observe that g0 is equal to f0 minus 0, which is greater than 0, and g1 is equal to f1 minus 1, which is less than 1, sorry, which is less than 0, since f1 less than 1. So now observe that g is continuous, and I mean now use, I mean look, g is continuous function, and at some point its value is greater than 0, and at another point its value is less than 0. So in between there will be a point such that gx naught is equal to 0, correct? And this implies what? This implies fx naught is equal to x naught. Understand?
Sir, this g of x function, how did we assume f of x minus x?
No, we're not assuming, we are taking gx like this. But making gx is
Okay.
equal to fx minus, it's a kind of trick. Understand?
And sir, for a decreasing function,
Sorry, for a
uh, for a decreasing function, this is for increasing function or decreasing function?
no, this is general, it is general situation. No increasing
Okay, okay,
decreasing
sir.
is there should. Only f0 not equal to 0, f1 not equal to 1, this implies f0 is greater than 0, f1 is less than 1. That's it. It has
Sir,
nothing to do with
only the domain of 0 to 1, this
yeah.
we can say about. If domain is different, we can't say.
Yeah. For example, consider the map x goes to x plus 1. So this function can't have any 6 point, right? I mean, obviously, domain R to R. So in general, it may not have 6 point, but on particular situation, it can happen. Understand? And by the way, one thing is that we find a x naught such that this. Okay, I mean it's common sense, but it's actually a theorem which is known as Bolzan's theorem. It says
Okay,
that
Bolzano-Weierstrass theorem.
no, only Bolzan's theorem. It is not Bolzano. It is only Bolzano's theorem.
Sir,
Bolzano
what does it
was
say and what is the importance?
yeah. This says that suppose f is a function from AB to R, continuous, and suppose f of a and f of b are of opposite sign, then this theorem tells that we can find the c belongs to open interval ab such that f is equal to, I mean if some point has negative value, some point has positive value, then obviously it has to cut the x-axis, right? So this implies f c equal
Yes,
to
yes,
0.
yes, yes. To change the sign, it has to cross at least once.
Yes, right. So yeah, so it's a theorem actually. this is known as the Bolzano's theorem. Okay. So one second. And by the way, one thing I should note that actually initially I have introduced a function dAx. Okay. The point is that dAx is 0 if and only if x belongs to a closure. Ravi, you should try it. Okay, by the way, let me define the dx. Dx is equal to infimum of the set x minus a. A belongs to a. This is the function dAx, and then dA is uniformly continuous, and you can show that dx is zero value, zero map if and only if if and only x belongs to capital A. Okay, so yeah, so you can try it, and please let me know on the next live meeting.
Please once explain the question. I will
Yeah.
repeat.
The question is dAx is a function which is defined as follows: infimum of mod x minus a belongs to a. Okay, this is the
Sir,
function.
D
D suffix ax. A is a subset of R.
so D of A means what?
It is not meaning. I mean, it's a function we're defining as follows. It's a definition of a function. Understand?
Okay, okay. And sir, this infimum part.
It's the definition is the infimum of mod x minus a belongs to a. That's it. It's the definition. Understand?
Sir, infimum of x minus.
Yeah, infimum of x minus
Okay.
a. I mean, infimum.
How we write it?
No, no. I mean, this is the way of writing.
Okay, okay,
There
sir.
is no explicit way. This is the way of writing. That's why the infimum of this thing makes. I mean, that's why I have written this infimum of that. Okay. Understand?
Okay, sir.
And you show that this is zero if and only if x belongs to a closure. This is the question. Okay.
Okay, sir. If and only x is element of A.
Closure. A closure.
Sir, once just say the language of the question, what is given and what is to prove.
Yeah.
That's it.
dAx is zero if and only if x belongs to a closure. This is the question.
If and only if x belongs to A bar.
Yeah. A closure. Okay.
Sir, this question is in assignment or in that session?
Sorry.
Sir, this question is there in the assignment?
No, it is not in assignment. Okay, you
sir.
understand. Okay, bye. I'm
Okay, sir.
leaving the call. Okay.
Thank you, sir. Hello, sir. Sir,
Yeah.
in the initial first hour, what did you teach, sir? I have missed that. So can you just
Yeah,
a 2-minute recapitulate?
Yeah, I've started with one second. You start with the you start with definition of uniform continuity, then state some theorems and solve some problems. Okay, no issue. I mean, I will upload this PDF in the Google Drive. and we'll share the link. I mean, NPTEL will share the link. I will share the NPTEL, so you can look
Okay.
at that
Thank
PDF
you.
from there. Okay.
Yes, sir.
Okay.
Thank you.